Hey guys, so I forgot to hit the record button on the lecture last night, so I decided I might come back and just record a quick, I guess I'll just record sort of the last half of the examples, the ones that are a little bit more confusing, the applications, some of the inequalities and stuff like that, just so that we don't completely lose that review, you know, so you guys have something to watch for some decent application examples. So anyway, this will be a shorter video. We'll just go over, we'll go over some inequalities, then we'll go over solving for variables, and then we'll do all the applications that we did on Thursday. All right, so to start out, we're going to start out solving inequalities. And as we saw in class the other day and in the book before, in order to solve an inequality, we just use the same tools that we use for equations, except for when we multiply or divide by a negative, we switch the inequality sign. So I'm going to start off by adding 1 to both sides, and that's to get rid of the 1 that's attached to that negative 3x. So then we're going to have negative 3x is greater than or equal, just greater than 3. Okay, now we're going to divide by negative 3, but we're also going to notice that that's a negative. And so when we divide or multiply by a negative, the inequality sign switches. So that we're going to do that right off the bat so we don't forget about it later, because that's something that I do all the time. So now our negative 3's are going to cancel, and this x will drop straight down. And then on this side, we have 3 over negative 3, which is actually equal to negative 1. So for this particular inequality, the solution is x less than negative 1. All right, in graph form, that looks like this. We have a 0, a negative 1. X is less than negative 1, so we have an open dot. And the tapered end of the inequality sign points towards the variable, which tells us that our arrow goes left towards negative infinity. All right, in interval form, we have negative infinity with a round bracket, and it goes all the way to negative 1, which is his right endpoint, and it's a round bracket again because it's an open interval, because it's less than but not equal to, right? Okay. So this guy. All right, when we first see this problem, we say, okay, looks like we're going to be dealing with some fractions. It's probably going to get ugly. It's probably going to eat up all my time. But before we do that, all we need to notice is that all three denominators, right? Whoops, that was the wrong pen. What we need to notice is that, let's see now, 15, the denominator, that's equal to 3 times 5, right? And so this 15 denominator, that completely encompasses both other denominators with its factors. And so if we multiply through by 15, otherwise known as 3 times 5, we'll be able to cancel all of the denominators and get rid of all of our fractions. And that's exactly what we want to do. So let's go ahead and do that. So if I multiplied through 15, right, we have 15 times 2 over 3, and so that is 15, which is actually 3 times 5, just like we wrote below, and we still have that times 2 on top and the 3 on the bottom, right? And so this fraction went here. So this fraction, I'm going to go ahead and multiply 15 into that, right? And so that's 5 times 3 times x. And I'm just writing out the factors of 15 so we can see what we're canceling out here, exactly what we're canceling out. Okay, so keep going. We have less than, and then 4 times 15. I'm going to leave that as 15 because it's easier that way, over 15. Okay, so now we're going to go out and cancel some things. On this first term, we can cancel the 3's. On the second term, we can cancel the 5's. And on this last term, we can cancel the full 15. All right, next line. Here, let me just erase this real quick. Next line. So what we have left here is 5 and 2 in the numerator. Only a 1 in the denominator, right? And so this is equal to 5 times 2, which is 10. All right, we have 3 times x. That is just 3x, right? The 5's canceled, so there's only a 1 in the denominator here. That is less than, we had 4 times 15, but the 15's canceled, and they left a 1 in the denominator, so this is just 4. All right, now we're back to our kind of standard place where we're going to use the addition and multiplication principles. I see that this guy is unwanted. We want to isolate that 3x, and so we're going to do so by adding 10 to both sides. Excuse me, adding the opposite of 10 to both sides, which is negative 10. Negative 10. All right, so the 10s cancel out exactly like we wanted them to, and then we have negative 3x is less than 4 minus 10, which is going to be negative 6. Okay, now we're going to divide by the negative 3 in order to get that guy, in order to get rid of that guy, right? Divide by negative 3. And before we even do anything else, I'm just going to draw a big arrow down here to remind me that this guy switches directions because we are dividing by a negative. All right, so we're going to cross those out, and the plain old x drops down. Over here we have two negatives, which cancel out, and then we have a 6 over 3, which is equal to 2. So we have x greater than 2. How do we graph that? Well, let's check it out. So we got 0, we got 2, whoops, sorry, that should be 2. We got 2. This is an x greater than, but not equal to, and so we have an open dot at 2 because we never actually reached that point. The larger end of the inequality is going to x, which means our arrow has to go to the right. It means that x is larger than 2, so this is our interval way over here. All right. In interval notation, we have a round bracket because this is an open side of the interval, 2, and that goes to positive infinity, which we give a round bracket to because we never reach infinity. All right. So that was the inequalities. Let's check out solving for a variable real quick. All right, so if you guys remember this from class the other day, we were solving for r. Just to switch it up today, let's go ahead and cancel that out and solve for a different variable. Not that it's going to make that much of a difference in this problem, but let's say we wanted to solve for n. If we wanted to solve for n, just like yesterday, right, we just divided both sides by those terms attached to n that we didn't really want over there, right? R times t, r times t. That cancels out the r times t, and we get n equals pv over rt. All right, so when it asks you to solve for a variable, all you do is consider the other ones around the variable, like coefficients or like just regular digits, and solve algebraically. Okay. This guy here, solve for t. This is an important one. You're going to see this one all the time. We have we have the variable that we want to isolate in two different terms that we can't really combine. We're going to have to factor it out. So, for this guy, let's see now. We want to toss the 2t over to this side, and we also kind of want to toss this x over to the other side, right? That'll give us both terms with our t's on one side and the terms without t's on the other side. So we're going to say k, right? If we subtract x from both sides, we get k minus x on this side. And then if we subtract 2t from both sides, we're going to get xt minus 2t. All right, so now we have this situation where we've got a t in each one of our terms on this side, and so we're allowed to factor that out. Okay, and so the k and the x stay the same, but the t's get pulled out, right? It's the opposite of distribution, and so the t goes outside the parentheses, and on the inside, the x and the negative 2 remain. All right, so now we're going to divide by the entire sum, x minus 2. And that's going to cancel on this side, and we're going to get t equals k minus x over x minus 2. And there we go. All right, so let's go on and tackle some of these pesky applications. All right, first problem is a perimeter problem. So for all perimeter problems, our general equation is perimeter equals 2w plus 2l. Why is that? Well, because a rectangle looks like this. Suppose we have this side as L and this side as W. the perimeter is the distance of all the edges, right? So we obviously have 2 L's and 2 W's to take account of, which is why we get 2L plus 2W in our formula. All right, so we wrote down our general formula. Now let's see what kind of variables we have. So right off the bat, we see that we have 92 meters of fencing total. That tells us that the perimeter needs to be 92 feet. Okay, in the next sentence, it says that the garden must be 4 meters longer than it is wide, right? And so that tells us that L equals W plus 4. Okay, there is a different way to do this problem. If you wanted to, you could say, well, obviously that means that W equals L minus 4, right? And you could proceed like that. I'm going to go with the W plus 4 just because it's totally okay to go with L minus 4. It just changes the problem slightly, but we'd get the same exact answers. Okay, so it doesn't tell me anything about width, and so we just say width equals width. All right, now all we need to do is plug these numbers in to this general equation and solve. So P equals 92, so I'm going to write 92 here, equals 2W, right? W just equals W, plus 2 times L. Now it's really important here that when we sub, right, this is supposed to be an L, but we're going to erase it and substitute W plus 4 in there. And it's really important that we leave our parentheses, or that we add parentheses here, W plus 4, because this means that we have to distribute the 2. If we didn't have the parentheses, this would be 2W plus 4. With the parentheses, it's going to end up being 2W plus 8, and that's a big difference. So the parentheses are very important when we're doing this. Okay, and parentheses usually don't hurt. And so if you're nervous, you're like, I don't know, maybe I should add parentheses, maybe I shouldn't. If it's a sum, it's probably safer to add them. All right. So first things first, we're going to get rid of these parentheses that we just added in there. We do that by distributing. So we have 92 equals 2W plus 2 times W plus 2 times 4, which is 8. That gives us 92 equals 4W plus 8. All right, if we subtract 8 from both sides, then we have 4W equals 92 minus 8, which is 84. All right, if we divide both sides by 4, then these guys cancel, and this is equal to 21. All right, so we have W equals 21. There we go. That is a basic perimeter problem. Variations on this problem might have you doing inequalities. You know, they might say, I don't know. They might say that they want to use more than 92 feet or 92 meters of fencing. You know, you might have something like that. But for now, it's just equalities. So anyway, triangles. The second angle of a triangular kite is 4 times as large as the first. The third is blah blah blah. Okay. So to handle this, you should recognize this already. This is the angles of a triangle. Angle 1 plus angle 2 plus angle 3 is equal to 180. So in class, I've been doing this with the angles. You guys have seen it done that way already, but maybe I'll just replace these with variables here, and that will, I don't know, maybe that'll help us out a little bit. So I'm going to switch the angle sign to just an X, right? Which kind of, it just looks nicer than the angle sign, really, in the end. So I'm going to say x1 plus x2 plus x3 is equal to 180. Okay. So now we go through and we read the problem one sentence at a time so that we can work out our relationships between our angles. So the second angle, we see here in the very first sentence, the second angle of a triangular kite is. That tells us that x2, which is angle 2, is equals 4 times the size of the first angle. So this is 4x1. All right. The second sentence, this tells us that the third angle is 5 degrees more than the sum of the other two angles. Okay, so we're going to say angle 3 equals 5 degrees more, right? 5 plus the sum of the other two angles, x1 plus x2. Okay, we reached the bottom, and they haven't told us anything about x1, so we just say x1 equals x1. Okay, so now what we really want to do here is we want to make sure that all three of these variables are in terms of just one of the variables, right? And so what we're doing here is we're boiling down 3 variables to a single variable, which makes it solvable for us. So we have all 3 variables here, and we want them all to be in terms of a single variable. x1 is definitely the variable that's going to be the best for us here, but we have one problem. We have an x2 over here. So what we're going to notice is that up here on the first line, x2 is actually equal to 4 times x1. So we're going to do a simple substitution. We're going to go ahead and erase this x2, and we're going to replace it with 4x1. Okay, so now we take our general equation, we fill stuff in, and then we solve. So x1, right, so x1 from the original, that's just equal to x1. No problem. x2, right, we plus x2. x2 is just equal to 4x1. And x3, of course, is equal to 5 plus x1 plus 4x1. All right, and all this is still just equal to 180. All right, when we combine these x1s, we're going to get 10x1 plus 5 equals 180. Okay, so now we're going to subtract 5 from both sides, and that's going to allow us to isolate that x1. Okay, now we have 10x1 is equal to 175. If we divide both sides by 10, we get x1 is equal to 17.5. All right, so the problem wants us to identify all the angles, so we're going to go ahead and do that. So x2, as we saw up here, x2 is equal to 4x1, and so we say x2 equals 4 times x1, which is equal to 4 times 17.5, which is equal to 70. Okay, then they give us x3, right? x3 is just equal to 5 plus x1 and x2. So all we need to do is add those guys up. 5 plus 17.5 plus 70, that's equal to 92.5. Now when we add all these guys up, 17.5 plus 70 plus 92.5, they equal 180. And that's our little check there. We know that we got that one correct. Okay, well, let's move on. Let's move on to our base plus rate times time equals total problems. Okay, so an unconditional acceptance into the MBA program at Arkansas State University will be given to students whose GMAT score plus 200 times the undergraduate grade point average is at least 950. Robin's GMAT score was 500. What must your grade point average be in order to be unconditionally accepted into the program? Okay, so let's go ahead and we have our base, plus rate times time equals total. Let's go ahead and try and fill this guy in, right? And this sentence is really the key to the whole problem, right? Okay. GMAT score plus 200 times the undergraduate grade point average is at least 950. That's the whole sentence right there, right? So that tells us GMAT plus 200 times the undergraduate grade point average rate. We're just going to say GPA is equal to x, right? Let x be GPA. So we're going to represent that by x. And then that equals our total, right? Which is 950. It has to be at least 950. So that's not really our total. What that is our limiting value. So we're going to erase this equal sign. We're going to put in the appropriate inequality. Okay, so it says the GPA plus the GMAT must be at least 950. That means that they have to be greater than or equal to 950. All right, so let's go down to the next line, and we note real quick that they've already identified what the GMAT score was. It's 500. So we're going to have 500 plus 200x greater than or equal to 950. All right, now we're going to subtract 500 from both sides, and that's going to allow us to isolate that x once again. So now we have 200x greater than or equal to 950 minus 500, which is, 450. All right, divide both sides by 200. All right, these guys will cancel out. And remember, we just divided by a positive number, and so this inequality in the middle does not change. If that were a negative number, it would change, but it's not, so it stays the same. So 450 over 200 is equal to 2.25. So that tells us that x must be greater than or equal to 2.25. All right, we look at the when we look at the original problem, they're asking about grade point average. That's what we defined x to be. And so we say that her grade point average must be at least 2.25 to get automatic acceptance into this graduate program. What does this look like on a graph? Cha-ching. We just make sure we label 0, right? We have 1, 2, maybe 3 over here. And then we have roughly 2.25 right here, 2.25. We notice that the inequality is a greater than or equals, which means we fill this in with a solid dot because it comes up to it and it can equal it. The variable is on the larger side of the inequality, right? That means that the variable x must be larger than 2.25, so our arrow points in the larger direction. And it goes to infinity. In interval form, this guy is 2.25 with square brackets because we can be equal to, and it goes to positive infinity. All right, set builder. Let's go ahead and throw one of those in just because it's going to be on the exam. Set builder would be x such that, and then we restate our solution such that x is greater than or equal to 2.25. There we go. All right, let's do a distance, rate, time problem. So, in October 2011, Mr. Ed Carpenter won the Kentucky Indy 300 with a time of 1:42:02 for the 300-mile race. At one point, Carpenter was 20 miles closer to the finish than to the start. How far had Carpenter traveled at that point? Now, some of you guys might be saying, well, they already told us it's just a 300-mile race, so if he's 20 miles closer to the finish than to the start, wouldn't he just be at 170 miles? Yes, you're correct. But if you just write down 170 miles on a test, I'm going to give you 0 points, which that would be a really bummer for me and you. So you got to figure out how to do this algebraically, right? And so this is a classic case of a double leg problem, right? So Carpenter has a total distance, right, which is 300 miles, and they split that total distance up into 2 different legs, and so we're going to come up with values for those 2 legs, and our general problem is going to be leg 1 plus leg 2 equals total distance. Okay. So to figure out what we're going to name our legs, it's probably going to help to draw a little diagram. So we're going to say this is the finish line. We're going to say this is the start line. And we're going to say this is roughly mid. Okay, so Let's see now. So for this guy, Carpenter's 20 miles closer to the finish, right? Which, let's just say this is 20 miles right here. 20. Okay, so this is where Carpenter is. So there's two ways to do this. We can either label the interval from start to Carpenter as X, or we can label the interval Carpenter to finish as X. I'm going to just do it Carpenter to finish. You know, if you did it Carpenter to start, then that would be fine. Your variables would just change a small bit, right? And maybe I'll just explain how that would look if you decided to do that. So if you were going to say this is X, start to Carpenter, then you would say let Carp's distance from start be X, right? Then you would say distance from finish was equal to X minus 20. Right? That's how you do it the other way. And then you would say, you know, and then you'd plug it in just like how we're supposed to do. You know, I don't know, I like to do it. Actually, since we did it the other way in class, maybe we'll just do it this way this time, right? Okay, so suppose we did do it this way. Then leg 1 would just be equal to X, right? Leg 2 would be equal to what we have right here, X minus 20. And the total distance is going to be 300. So, now that you have your two legs written down, we just combine like terms and go from there. So this is going to give us 2x, 2x minus 20 is equal to 300. All right, so this means we can add 20 to both sides. We get 2x equals 320, which of course we divide both sides by 2 now to change that into a 1. We get x equals 320 over 2, which is actually equal to 160. So that tells us, right, since we labeled the distance from the start to be x equals 160, oh, and that's actually what they were asking in the first place, how far Carpenter had traveled. So that's really the best thing to name x anyway. If you had named x as this distance, the distance to the finish, like over here, then you'd have to do a little bit of extra math at the end, right? You'd find x, and you'd have to actually add 20 to it to find, oh, you'd actually have to add 40 to it to find his current position, I think. Yeah, so anyway, things change a little bit when you swap where your variables are. You just have to make sure that you're solving, that in the end you have solved for what they've asked you to solve for. Okay, so let's see now. Let's do an average problem. So, in order to qualify for a batting title, a Major League Baseball player must average at least 3.1 plate appearances per game. For the first 9 games of the season, a player had 5, 1, 4, 2, 3, 4, 4, 3, and 2 plate appearances. How many plate appearances must the player have in the 10th game to average at least 3.1 per game? All right, so what they're saying here is that average must be greater than or equal to 3.1. Okay, so we've got everything here. All we need to do is come up with our expression for the average, right? And so an average of any numbers, right? The average of 1, 2, 3 would be 1 plus 2 plus 3 over 3. There's a 3 down here because there are 3 digits up here, right? So that's how you do an average, right? You add all your digits up and then you divide by the number of digits. So let's do this for this example. So we have 5 plus 1 plus 4 plus 2 plus 3 plus 4 plus 4. This is getting tedious. Plus 3 plus 2. And then our final game, our unknown game, is x. Now we divide all that by the number of terms. There are 10 terms. Greater than or equal to 3.1. Okay, on the next line, we're going to sum all those terms on the top, and those are equal to 28. Right? We still have our x right here, so it's 28 plus x over 10 equals, oops, not equals, let's go back. Not equals, but is greater than, must be greater than or equal to 3.1. All right, we want to get rid of this 10 in the denominator, which will allow us to free up our x in the numerator. So to do that, we're going to multiply both sides by 10. All right, the 10s on this side cancel, and we get 28 plus x greater than or equal to 3.1 times 10, which is 31. All right, if we subtract 28 from both sides so that we can isolate this x, minus 28, then we get x is greater than or equal to 31 minus 28, which is 3. Okay, graph form, 0, 3, solid dot because it can be equal to, and the larger end opens towards the variable, which means that the variable is on the larger side of this, and it goes to positive infinity. Interval form, this is 3 with a square bracket because it can be equal to, and then infinity with a round bracket because we never equal infinity. All right. Let's keep going. How about the evaluation problem? Okay, so, you know, I mean, I wrote evaluation up here, so we're already keyed in, but not all evaluation problems actually say the word evaluation in them. But it's easy to recognize them because usually they give you a bunch of variables and then they give you a bunch of values for those variables and just tell you to solve for one. So they tell us right here the wavelength W in meters per cycle of a musical note is given by W equals R over F, where R is the speed of sound in meters per second, F is the frequency in cycles per second, and the speed of sound in air, and so they're starting to give us our variables here. So they're saying now the speed of sound in air is 344 meters per second. That tells us that R is equal to 344, right? Meters per second. We're not going to worry too much about the units. The next sentence tells us what is the wavelength of a note, right? So they ask what is the wavelength? So we know that we're solving for W. What is the wavelength of a note whose frequency in air is 24 cycles per second? All right, so now they've given us F. F is equal to 24 cycles per second. All right, now all we need to do is solve this guy, right? And so W equals R over F, which is equal to 344 over 24, which is then equal to, okay, so this is roughly equal to, or is exactly equal to 14.3 repeating. We could have also probably reduced this, and I definitely would have accepted that as well. Okay, so let's go down to the percent change, right? So the percent change, recall that it's always sort of set up like this. It's as so. It's original plus change times original, and that is equal to the new value. So before we even read our problem, we're just going to write down original, change, and new, because those are the three values that are crucial to this. All right, so right off the bat, the first sentence says, after a 25% reduction. Okay, that tells us right off the bat that our change is negative 25%. 25% reduction. A picnic table is on sale for $120. So after the reduction, the sale is $120. So that tells us that the original is unknown, and our new is after the sale, which is going to be $120. And our original, the unknown, right? They asked what is the regular price, aka the original price. That's just going to be X. All right. So now let's just fill in our values, right? The original price, X, plus the change, which is negative 25%, also known as negative 0.25, right? If we change our percent to a decimal, that's what we get, multiplied by x, and that equals the new value, which is 120. All right, so x minus 0.25x is 0.75x. That's still equal to 120. And if we divide both sides by 0.75, then we get 160. So the regular price, the original price, was $160. Okay, so that's it. That's a percent change problem. So that's about the review we did. You know, I know we went over some easier stuff, but I'm assuming that you guys can study that stuff on your own. So this is a much shorter little lecture here, but we went over the general kinds of word problems. Keep in mind that just because you didn't see a word problem on this review doesn't mean it won't be on the test. Right? If we went over it in the last couple of chapters, it's totally valid to throw it on the test, whether I am putting it on the review or not. Which is kind of lame. I don't think I'd do that, but you never know. Sometimes maybe I'd forget or space out and accidentally do it. So make sure you study all those problem types, not just the types that I have on the review. Besides that, just make sure you schedule your appointment in the testing center. Remember, the test will be available during testing center hours, Monday and Tuesday. Conan does take a short lunch, so make sure you schedule it in the morning or early afternoon if you want to give yourself extra time. That's about it. So I hope you guys have a great weekend, and I will be recording and posting a lecture for next Wednesday's class online, but I should be able to make next Thursday's class, just barely. So we will hopefully see you in the Student Center today, and have a good weekend.